Alright, welcome back everybody. In this video we're going to look at the examples from our mean value theorem lesson. Make sure you've read through the text on the first page of this lesson and you know what the mean value theorem is. And then it'll be a little bit easier for us to approach these examples. Alright, example 1. Verify that the function f of x equals x cubed plus 2x squared minus x satisfies the hypothesis of the mean value theorem on the interval from -1 to 2, then find all values of c that satisfy the conclusion of the mean value theorem. Okay, so to satisfy the hypothesis of the mean value theorem, this function has to be continuous on the entire closed interval from -1 to 2, and it has to be differentiable on the open interval from -1 to 2. Both of those things are true. We know that all polynomial functions are continuous everywhere in their domain, or really for all real numbers, and we know that all polynomial functions are differentiable for all real numbers, so they're going to be both continuous and differentiable on this closed interval, since it's a subset of the real numbers. Alright, then we want to find all values of c that satisfy the conclusion of the mean value theorem. And a refresher, the conclusion of the mean value theorem is that f prime of c is equal to f of b minus f of a all over b minus a for some c in the interval from -1 to 2. So the first thing I'm going to do, I'm going to find f prime of x, and that's equal to 3x squared plus 4x minus 1. And then to find these values of c, we want to put c into that function for x. And that's going to be equal to f of 2 minus f of -1 all over 2 minus -1. And so we need to find the values of the function at 2 and at -1. We substitute 2 into the original function. That's 2 cubed is 8, plus 2 times 2 squared, that's 8 more, that's 16, minus 2, it's going to be 14, is going to be the value of f of 2. The value of f of -1 is going to be -1 plus 2 plus 1, so that's going to be 2. And so we're looking for values of c such that 3c squared plus 4c minus 1 is equal to 12 over 3, which is equal to 4. And I'm going to go ahead and solve this equation to find the values of c in that interval. And from here I can solve using the quadratic formula or, factoring if it's applicable. I'm going to go ahead and solve this equation on my calculator. Go into my y equals screen, and I'll graph 3x squared plus 4x minus 5. And since we're looking for the values where this is 0 on the interval from -1 to 2, I'm just going to set up my window to run from -1 to 2, because then I'm only going to get values that I'm interested in. And we see there's a value there. We were guaranteed a value by the mean value theorem since this function met the hypothesis of the mean value theorem. So we're looking for that 0. And looks like that value is 0.786. So c equals 0.786 is a value of c in the interval from -1 to 2 that satisfies the conclusion of the mean value theorem. Alright, on to example 2. For g of x equals x minus 4 over x minus 3, decide if we can use the mean value theorem for derivatives on the interval from 0 to 5, or on the interval from 4 to 6. If so, find c. If not, explain why not. So let's start with the interval 0 to 5. Can we use the mean value theorem on this interval? And we cannot, because g of x is discontinuous in this interval. At x equals 3. Why is it discontinuous at 3? Well, because the value of x equals 3 makes the denominator equal to 0, therefore it's discontinuous there. So we cannot apply the mean value theorem for derivatives in that interval. But in the interval from 4 to 6, we have no discontinuities, no lack of differentiability in that interval, and so we can apply the mean value theorem there. So we want to set up f prime of c is equal to f of b minus f of a all over b minus a for this interval. And so we've got, let's see, we need to I need to find g prime of c, and let's make all those g's. Alright, so first I need to find g prime of x. G prime of x is the derivative of this function. So low times the derivative of high minus high times the derivative of low all over low squared. Simplifying this, we find that g prime of x is equal to 1 over the quantity x minus 3 quantity squared. And so we want 1 over the quantity c minus 3 quantity squared is equal to, and now I need g of 6 minus g of 4 all over 6 minus 4. 6 minus 4 is 2. G of 6 is 2 over 3. G of 4 is 0. Okay, and so we have 1 over the quantity c minus 3 quantity squared is equal to, that's going to be 1/3. Don't even know if I need my calculator for this one. We've got c minus 3, the quantity squared, is equal to 3, since the denominators have to be equal. And so c is equal to 3 plus or minus the square root of 3. We just took the square root of both sides and then added 3 to both sides. Now, only one of these is in the interval from 4 to 6, and that's the one that is 3 plus the square root of 3, which is approximately 4.732 is the value of c in the interval from 4 to 6 that satisfies the conclusion of the mean value theorem. All right. Talk a little bit about increasing and decreasing functions there. Turn the page. All right. Example 3. Find the intervals on which the function is increasing and decreasing. Okay, so we're told in this corollary that if f prime is greater than 0, then f increases. If f prime is less than 0, then f decreases. So in order to find the intervals on which this function is increasing and decreasing, I'm first going to find f prime, and then I'm going to look at where it is positive and negative. So I take the derivative. Y prime is equal to 3x squared minus 18x plus 24. And I'm looking for where this is positive and negative. And a good way to find out where a function is positive and negative is to first look at where it's 0. So if I set this equal to 0 and solve for x, and this is one I can actually do pretty easily by factoring, I can divide everything by 3, gives me this function, and so x is equal to 2 and x is equal to 4 are the zeros. What I'm going to do now, and this is the first time we made one of these, we're going to make a sign chart for the derivative of the function. The derivative is 0 at 2 and 4, so I'm going to put those 2 points on the sign chart as zeros. And then every interval that's subdivided out on this number line is going to be either entirely positive or entirely negative. And so what I can do is I can substitute x values that are in those intervals into the derivative to figure out, and actually I can even substitute them into the reduced form of the derivative, to figure out if this interval is positive or negative there. So for the interval to the left of 2, I'm just going to go ahead and put 0 into this. So I put 0 into the x squared minus 6x plus 8. and it gives me positive 8. That's a positive value. That means all the values of the derivative in that interval are positive. From 2 to 4, I'm going to put 3 in here, and that gives me 9 minus 18 plus 8. That's negative 1. And so all the values in this interval return a negative value for the derivative. And then I'm going to put 5 in for this end interval. That's 25 minus 30 plus 8. It's positive 3. So the derivative is positive for all values of x in this interval. Now don't just assume that these positives and negatives are going to alternate like this. That's not always the case. Alright, so this function is increasing when on the interval from negative infinity to 2 and on the interval from 4 to infinity. Why? Because those were the locations where the derivative was positive. And it is decreasing from 2 to 4, because that was a location where the derivative was negative. And that's how we can use the derivative to find intervals where a function is increasing or decreasing. A lot of other information for you to read through in this lesson. There's a little pick here under corollary 3. Functions with the same derivative differ by a constant. So if I have a function and another function that has the same derivative, see how I do on this, these two functions differ by a constant value. In other words, the distance at any x value between these two functions should be the same. And that was a quick hand-drawn sketch, so it's not the greatest thing in the world, but basically that's an important piece of information for us. If the derivatives of these two functions are the same everywhere, then those two functions differ by only a constant. So this was our constant value there, and this was our function f of x, and this was our function g of x. And since they have the same derivative everywhere, they differ by a constant value at all moments in time, or for all values of x. Alright, that's the end of this video. See you guys next time. Have a great rest of your day.